What if I told you that the Coca-Cola you hold in your hand may have traveled through an industrial system capable of producing billions of servings every day? One bottle looks simple, but behind that dark liquid is a carefully controlled chain of purified water, sweetener, caramel color, acid, caffeine, secret natural flavors, carbon dioxide, packaging, and relentless quality checks. And here's what nobody tells you. There isn't one giant Coca-Cola factory making every bottle in the world. The Coca-Cola system uses local bottling partners that prepare, package, distribute, and sell the finished drink in markets around the planet. Today, the scale is almost impossible to picture. The Coca-Cola system reported 33.8 billion unit cases across its beverage portfolio in 2025, while the company says its brands account for about 2.2 billion servings every day. That means somewhere in the world, while you're watching this sentence, production, packaging, transport, or selling is already happening. So imagine walking through one of those plants with me, starting where the ingredients enter and ending where a perfectly sealed bottle races toward a truck. And before the first bottle gets filled, something even more important happens. The factory has to make ordinary ingredients behave exactly the same way day after day. Water must meet strict specifications, sugar must dissolve consistently, the beverage base must blend accurately, and carbon dioxide must create the familiar fizz. The flavor itself remains partly hidden because Coca-Cola identifies its natural flavor blend as a trade secret. So we're about to see almost everything that happens, except the one part the company deliberately keeps behind the curtain. Our journey starts with water because it makes up roughly 90% of Coca-Cola. But the factory cannot simply pump water into a tank and start filling bottles. Water treatment removes unwanted substances and adjusts the water so its safety, mineral content, taste, and consistency fit the production specification. In Coca-Cola bottling operations, treated water forms the foundation for the syrup and the final beverage, so every change in the incoming water has to disappear before the consumer ever notices it. Next comes the sweetener, and this is where geography changes the recipe's ingredient label. In Pakistan and many other markets, Coca-Cola Original lists sugar, while the US version lists high fructose corn syrup. Mexico's version uses cane sugar. The basic purpose remains the same: provide sweetness and body, but the exact sweetener depends on the market and local supply chain. A 12-ounce US can contain 39 grams of sugar, while Coca-Cola Pakistan lists 10.6 grams of sugar per 100 milliliters for its classic product. Then come the ingredients that create Coca-Cola's recognizable character: caramel color, phosphoric acid, caffeine, carbon dioxide, and natural flavorings. The label tells you what belongs in the drink, but it does not reveal the precise natural flavor recipe that creates the signature taste. That secrecy is deliberate, and it has survived since the drink first appeared in Atlanta in 1886. The original beverage began as a syrup mixed with carbonated water at a soda fountain, but today's manufacturing system turns that simple idea into a highly automated industrial process. But here's the hidden supply chain challenge. The factory needs ingredients in huge quantities without allowing their quality to drift. Sugar arrives by truck or other bulk transport, packaging materials arrive separately, and food-grade carbon dioxide comes from qualified suppliers. The company specifically identifies beverage-grade carbon dioxide as the approved grade for its carbonated beverages. Even the air around the production equipment matters because hygiene, contamination control, and temperature can affect the final drink. Environmental pressure makes the raw material story even more complicated. Water becomes both an ingredient and a critical manufacturing resource, while packaging adds another major material stream. Coca-Cola has been redesigning some PET bottles to reduce their weight, with a US and Canada redesign moving certain bottles from earlier designs toward 18.5 grams while maintaining required performance. The company also says its packaging strategy aims to increase recycled content and improve collection, showing that the bottle itself has become part of the engineering challenge. Now the ingredients are ready, but nothing has become Coca-Cola yet. They are separate streams waiting for one controlled transformation. The next room contains tanks, pumps, filters, sensors, and mixing systems where water and sweetener become syrup before the beverage base joins the mixture. And once that syrup enters the final blending system, One tiny mistake in proportion could change the taste of an entire production run. That's where the factory stops behaving like a warehouse and starts behaving like a precision machine. First, the factory prepares simple syrup by dissolving sugar into treated water and filtering the mixture to remove impurities. Coca-Cola bottling documentation describes this syrup as the starting point before the factory mixes it with concentrate or beverage base to create the final syrup. The tanks hum, pumps push liquid through polished stainless steel lines, and sensors constantly watch flow and composition. Industrial production does not rely on someone standing beside a tank with a spoon. Automated controls keep the recipe moving with repeatable precision. The simple syrup then meets the beverage base. And this is the moment when the factory creates the recognizable foundation of Coca-Cola. The exact flavor formula stays secret, but the public ingredient list confirms the presence of natural flavors, caramel color, phosphoric acid, and caffeine along with a sweetener and carbonated water. The acid brings brightness and tartness. Caramel creates the familiar dark appearance, caffeine contributes bitterness, and the flavor blend creates the signature profile. Think of it as an orchestra where you can see most of the instruments, but the conductor's private score remains locked away. Now comes an important point about temperature. Some Coca-Cola bottling processes use thermal treatment for specific products, while sparkling Coca-Cola follows a different route based on treated and cooled water before carbonation and filling. Public Coca-Cola bottling sources do not publish one universal temperature, pressure, RPM, or residence time for every Coca-Cola factory, because plants, products, packages, and equipment differ. So rather than inventing secret factory numbers, we can follow the publicly documented sequence. Treat the water, prepare the syrup, cool the beverage, carbonate it, fill it, seal it, inspect it, and package it. Then carbon dioxide enters the story. Carbonation means forcing purified CO2 into the beverage under controlled conditions so the gas dissolves into the liquid and later escapes as bubbles when you open the bottle or can. Temperature matters because colder liquid generally holds dissolved CO2 more effectively, while the carbonation equipment monitors pressure and flow to keep the process stable. The exact Coca-Cola plant settings remain proprietary, but the engineering principle is simple. Control temperature, pressure, gas flow, and dissolve CO2 so the finished drink produces the expected fizz. And now the liquid finally looks like the drink you know. The carbonated beverage travels rapidly toward the filling machine, where thousands of containers can move through the line in a continuous stream. The machine positions each bottle or can, delivers a precisely controlled fill, and immediately seals the package to protect the carbonation. Every second matters because the drink must stay cold and stable enough to preserve the desired level of dissolved gas while the container closes. For PET bottles, another remarkable process happens before filling. Coca-Cola explains that PET bottles begin as tube-like preforms made by injecting heated liquid resin into molds, after which machines stretch and inflate those preforms into their final bottle shapes. That transformation happens incredibly fast, turning a small plastic preform into a lightweight container engineered to hold a pressurized carbonated drink. And because the bottle must survive filling, transport, stacking, and opening without losing its shape or carbonation, packaging becomes a mechanical engineering problem of its own. The final packaging stage looks almost unreal. Filled bottles and cans rush through capping, labeling, coding, inspection, and multipack equipment without human hands touching every unit. Some plants package drinks in PET, glass, or metal cans, while refillable systems collect certain bottles, clean them, inspect them, and send them back into circulation. A single line can therefore combine liquid engineering, robotics, packaging science, machine vision, and logistics into one continuous production rhythm. At this speed, human eyesight alone cannot inspect every container. That's why modern bottling plants use electronic inspection systems that examine bottles for irregularities and reject units that fail the programmed checks. Coca-Cola bottling operations describe systems capable of detecting even tiny irregularities on refillable bottle lines, while broader production controls monitor key stages throughout the process. The machines do the repetitive checking thousands of times, but people still oversee the system and investigate anything unusual. Quality starts long before the final bottle. The factory checks incoming water, sugar, concentrate, flavors, packaging materials, and carbon dioxide before they enter production. During manufacturing, operators and automated systems monitor the blend, carbonation, filling, sealing, and package condition. Coca-Cola bottling operations cite international systems including ISO 9001 for quality management and ISO 22000 for food safety, alongside Coca-Cola's own quality and food safety requirements. Now imagine what happens when a bottle fails. A camera may notice an abnormal shape, a sensor may detect an incorrect fill, a system may identify a damaged container, or an operator may catch a strange vibration before the software does. The factory does not need to publish a universal rejection percentage because that number changes with the line, package, product, and operating conditions. What matters is that the inspection system can remove suspect units before they reach a truck, store, restaurant, or your refrigerator.